So that's the nucleus. Isotopes is a thing to do with the nucleus. And it has to be said that, by and large, as chemists, we don't care about the nucleus. Because the nucleus is in the middle of the atom, and the electrons are around the outside. And as chemists, what we're interested in is the way that one atom interacts with another atom to do a chemical reaction. And so if two atoms sort of are swimming around somehow and they bang into each other, it's not going to be the nucleus, the nuclei, which are the things which bang into each other. It's the bits on the outside, yeah? It's the electrons. And so chemists are concerned about electrons, not so much about protons and neutrons, and so we're not really going to come back to protons and neutrons very much at all, except maybe for a little bit right at the end. What we're going to care about an awful lot is the electrons, because these are the things which mediate the interactions between atoms to make molecules. As we've already said, the electrons are around the outside of the nucleus, but what we find is that they are arranged in groups. They don't all just randomly do their own thing like the planets. You have, each planet has its own orbit and it kind of does its own thing, and some are in the plane and some are out, and they're just all kind of independent. Electrons exist in little groups, and these groups of electrons live in things called orbitals. And so what we want to do for a little bit now is talk about these orbitals. Orbitals are just regions in space where electrons live. And you can get different sorts of orbitals in that some you can get different shapes and you can get different sizes. And different types of orbitals can hold different numbers of electrons. And so this is quite different from Rutherford's first proposal that they were all just spinning around the outside. And to be fair, it's a bit different to what they do a lot, certainly in level 2 chemistry, this business about the sort of the stack of pancake things with all these concentric rings and dots and stuff. We're going to go beyond that a bit, right? But this final statement here is important, and it's going to get me in trouble with the chief marker of NCEA level 3 chemistry, because he apparently came out, well, I saw it was in the paper last year. He said, students will lose marks if they anthropomorphize their molecules. Right? In other words, you can't say your molecules are happy or sad or excited or any of this sort of thing. Right? I'm here to say, first of all, you've probably guessed, this isn't NCEA anymore. Yeah? You're not in Kansas anymore, sort of thing. We don't care. It doesn't work that way at university. And I will talk about happy molecules all day long, and you should feel free to do so as well. Right? If by saying that the molecule's happy, you understand that that means it's stable or low energy or any of these other more nebulous terms, if you understand that a molecule will want to do something in order to be happy, then that's fine with me, because you're understanding fundamentally what drives chemical reactions. Right? So long as you know what happy means, then you can say that the molecules are trying to be happy, and that'll be fine. Right? So filled orbitals are stable orbitals. So if you have an atom with filled orbitals, then it's happy. And this is a very big driving force for a lot of chemistry. This trying to make the atoms happy by them filling up their orbitals with electrons. Yeah? So what are these types of orbitals? There's one called an s orbital. And an s orbital is spherical, so it's like a ball. And an s orbital contains 2 electrons. So we have a ball. At the center of that ball is where the nucleus is. And within this ball, you can have 2 electrons zooming around. Right? Now, they're not constrained to be on the surface of the ball or a particular place within the ball. They are just somewhere in the ball. So that's an s orbital, and you might think, oh, well, it's s because it's spherical. Well, unfortunately, that doesn't work, because the next one's called p orbitals, and they don't look anything like p's. In fact, the first one kind of looks like a P if it was green, but this is a P orbital, and so a P orbital, if you read the textbooks, it says that it's dumbbell-shaped. So it has two lobes, as they're called, or two ears, if it was sideways. One up here and one down here. The nucleus lives in the middle here, right? So at that point, the p orbitals don't exist, right? There's a distinct gap in the middle here where the nucleus is. So the electrons are either over here or they're over here. And you could say, well, if they're over here, how do they get to being over there if they can't go through the middle? And that's a very good question, but it's physics. So we won't go there unless you really want me to. So they're dumbbell-shaped, nucleus is here. They come in groups of 3 because you can see that I've drawn this one pointing up, but I could just as easily have drawn it pointing sideways. It would still be the same shape, it'd just be pointing in a different direction. And it turns out that these come in groups of 3, and so we call them the px, the py, and the pz orbitals based on Cartesian axes. Yeah? So x, y, and z, like on a graph. And so they're all at 90 degrees to each other. Or if you like, they are mutually orthogonal. Yeah? So they're all at 90 degrees to each other. And so that's why they come in groups of 3. You have a px, you have a py, and you have a pz. And each of those orbitals, the px, the py, and the pz, can contain 2 electrons. Right? So if you have a group of p orbitals that's a group of 3, then in total you can put 6 electrons in that group. Does that make sense? Yeah? Please feel free to yell if I'm starting to hurt your heads. So you've got s orbitals, you've got p orbitals, and then there's also things called d orbitals. See, they're getting more complicated. D orbitals are mostly that shape, so they're kind of like 4-leaf clover shape. Again, the nucleus is in the middle. And these come in groups of 5. And again, each of these d orbitals in the group of 5 can contain 2 electrons. And so, as a whole, the group of d orbitals can contain 10 electrons. Right? So s orbitals come by themselves. And so you can put 2 electrons into each s orbital. P orbitals come in groups of 3. And so in total you can put 6 electrons into a group of p orbitals. D orbitals come in groups of 5. And so in total you can put 10 electrons into a group of d orbitals. Each individual orbital only ever has 2 electrons in it. Yeah? Okay. There are also things called f orbitals, which again we almost never talk about in chemistry because they're associated with these elements that lurk at the bottom of the periodic table. Those ones that sort of seem like they've fallen off the bottom, and you almost never get lectures about or get taught about, even though uranium's in there, which is kind of important. F orbitals are associated with those, so we're not going to do anything with Fs at all. Yeah? Okay, so you have these 3 different types. They're different shapes. They come in different sized groups, either sort of solitary ones or in groups of 3 or in groups of 5. And then the other thing to know is that they come in different sizes. And so you can have different s orbitals of different sizes. You can get bigger or smaller versions of the same type of orbital, and the difference in size is related to the energy of the orbital, or if you like, the energy of the electrons in the orbital. And the rule here is that the bigger the orbital is, the higher in energy it is. And so if you have electrons in a bigger orbital, they have more energy than electrons that are in a smaller orbital. Right? And if you like, one way I like to think about this is if you imagine you have a balloon and you start blowing up a balloon, then it starts off being little, and you can think about it being relatively low energy, but as you blow it up more and more and more and more and more, it becomes more and more likely to explode and pop, yeah? And so as it gets bigger, you can think about it being a higher energy thing and more unstable, yeah? Because it's about to pop. So this is the same thing. As the orbitals get bigger, they're getting higher in energy. The electrons in them are gaining more and more energy. And so here's a couple of examples. You can have what we call a 1s orbital. That's going to be the smallest, lowest energy s orbital you can have. And then you can have something called a 2s orbital, which is bigger. It's still an s, so it's still spherical. It still contains 2 electrons. It's just bigger, so those electrons have more energy. Yeah? And what you can do is you can use something called quantum mechanics, which we're not really going to do at all, and we don't really do in Chem 191 either, to be fair, but if you brave it out and come to second semester chemistry, we spend quite a lot of time talking about quantum mechanics and talking about where this result comes from. For the moment, you just need to know the result. You don't need to know how we got it. This is the set of all the orbitals that a particular atom has at its disposal to put electrons into. Right? So it starts at the lowest energy one on the left, which is the 1s. So the lowest energy orbital that you can put electrons into on an atom is a 1s orbital. Then, if you've still got some left over, they go into the next lowest energy orbital, which is a 2s. And then, if you've still got some more left over, then they go into the so-called 2p orbitals. And remember, that's a group of 3. That px, py, pz, right? So this is a group of 3 orbitals. Then if you've still got some electrons left over, they have to go into a 3s, then into a 3p, then into a 4s, and then for some reason a 3d, and then a 4p, and so on. This may make no sense to you. But, well, I can explain it to you if you like, but you'll need half an hour, and it's completely irrelevant to the course at hand, right? The thing you need to know is you need to know this order. And you probably, well, if you learn all of that, if you learn up to 5s, then you're certainly fine for anything I'm going to ask you in Bridging Chem, and certainly anything you're going to see in Chem 191, right? What we can then do is we can write below that how many electrons we can put into each of those different types of orbitals, right, using these little rules that we learned on the previous slide. So we can say that the 1s orbital can contain 2 electrons. That little E minus is a symbol for an electron with a negative charge. Yeah? The 2s orbital can have 2 electrons. The 2p orbitals as a group can contain 6 electrons. The 3s orbital contains 2 electrons. The 3p orbitals as a group contain 6, and so on and so on. Yeah? Once we have all that memorized, then what we can do is we can write something called an electron configuration for any particular atom that we might be given, right? And this is key to understanding how the chemistry of a particular atom will work. Because remember I said it's all about the electrons. This will tell you what electrons you have in what orbitals, or more correctly, which electrons you have in which orbitals. Yeah? And so what we do is, first of all, we work out how many electrons a particular atom's got. How do we do that? We look on the periodic table, which you will always have at hand, because you don't have to memorize it. Yeah? And we can look up on there, and we can look for the atomic number, because remember the atomic number is the number of protons in the nucleus, but for a neutral atom it's also the number of electrons. So that will tell us how many electrons an atom's got. And then what we do is we just start putting them into our series of orbitals that we've learnt until we run out. Yeah? And we put them in that particular order. So, if we were carbon, you can look up and see that carbon's got 6 electrons. And so we would write its electron configuration like this. We would start off with 1s, the lowest energy orbital, and we put 2 electrons in there. and then that's full. We can't put any more in the 1s because it can only have 2 electrons in it. So then, because we've still got some electrons left over, because we've got 6 in total, then we put some into the next lowest energy orbital, which is 2s, and we fill that up by putting 2 electrons into it. And then we've still got 2 electrons left over, and so those 2 have to go into the 2p orbitals. Right? The 2p can have a total of 6, but we can't fill those up, we've only got 2 left over, and so we put our remaining 2 electrons into those 2p orbitals, and so we end up with an electron configuration of 1s2, 2s2, 2p2. Yeah? And that's it. Now some of you are probably going, do they both go into the same p orbital, or does one go in one and one go in another? The answer is probably one goes into one p orbital and the other one goes into a different p orbital, but that's not really important for us at the moment. Right? We don't have to be that specific when we're writing an electron configuration. We just need to know what types of orbitals the electrons are in. Right? So for carbon, we would say that it's 1s2, 2s2, 2p2. Does that make sense? Yeah? Here's another one. Here's chlorine. Chlorine has 17 electrons, and so we do the same thing. We start at our lowest energy orbital, which is the 1s. We fill that up, and we move on. To the 2s, fill it up, move on. 2p, fill it up, move on, and we keep going until we've run out of electrons. Right? And if we do that, then for chlorine, we end up with 1s2, 2s2, 2p6, 3s2, 3p5. Yeah? And then, some which I haven't already done, have a go at those two. And so that one would be vanadium. So vanadium has got 23, so it's quite a lot. And so that means that we get all the way up to the 3d orbitals in order to have enough orbitals to take that many electrons, right? So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. It's important to remember that that 4s comes before the 3d. There's all sorts of interesting reasons why that is, that again aren't important for us now unless you want to come and ask me about it. But you just, again, need to remember that order. Okay? There'll be some more of these to practice, I think, in the tutorial this morning. And so the little final thing to get us to our chocolate biscuits is this. It turns out that a large part of chemistry is about electron configurations because it is the electrons which determine the ways in which an atom can interact with other atoms to make molecules, right? So now what we're seeing is that not only is it the electrons which interact with the electrons on the other atom, but because the electrons live in orbitals and the orbitals become increasingly big, then it's going to be the electrons in the biggest orbitals, which will be the ones that interact with the electrons in the biggest orbitals on the other atom, right? It's kind of like onions. If you imagine two onions, onions are made up of layers, yeah? And so if you think about each of those layers being like an orbital, then when you roll two onions together on the bench, it's the outermost layers that bang into each other, not the inner layers, right? And so in the same way here, it's going to be the electrons in the outermost orbitals, the biggest ones, that are going to be the ones which are most important in determining how an atom interacts with other atoms to do chemical reactions.